Recording in progress.
All right, good afternoon, everyone. This is more or less the continuation of yesterday's lecture. Um, and I've got some new things to highlight, and I'm definitely going to do that. But for this lecture, I want to just kind of elaborate upon some of the topics that we've already discussed. And I'm going to do another example. So whenever I say do another example, what I want to do is I want to take this amino acid over here, tyrosine. And with tyrosine, what I'm going to do is I'm going to go through and draw a titration curve indicated over here. And then I'm going to do a PI calculation, PI calc. And then, just for the sake of the fun of it all, I'm going to draw different forms of this molecule. And then last but not least, um, I'm going to do a basically a question of what does it look like predominant form? What's the predominant form at X pH or pH of X? So the first thing that I want to do is draw a titration curve for tyrosine. Now, tyrosine is an amino acid that has a single letter code of Y and has a three-letter code of TYR. Now, over here, what you'll notice is the table that corresponds to all of our different pKa values. We have Y, it's got three pKa's, 9.11, 2.20, 10.07. Now, with that, one of the things that I want you to be able to do is, like, as I mentioned previously, I don't expect you to have pKa values memorized. However, what I do want you to be able to do is to be able to look at a structure and look at pKa values and make an approximation as to which one is which. So whenever I look at any amino acid, I'm going to look at my backbone and I'm going to say, here is my N termini, here is my C termini. I expect my N termini to have a higher pKa and a C termini to have a lower pKa. I've got 9.11, 2.20, and 10.07. Now, this is a little bit tricky because 9.11 and 10.07 are fairly close together. But if I keep in mind that the N termini is typically around 9, I'm going to go ahead and just say, well, I'm guessing this is 9.11. Now, if you look at the table, you can see pKNH3, well, it is 9.11. That's the column. But I want you to, when you see a table that doesn't have these explicit um, designations, you'll be able to recall and say, okay, this is what I think that it is. Next is my carboxylic acid, which is 2.20. And then my R group, which is my third pKa that I'm left with, which is about 10.07. So I always go with my N termini is about 9 and my C termini is about 2. And that rule of thumb is going to help me out quite a bit. So it's going to help me identify those values. Now that I've identified my pKa values and assigned them, one thing that I also want to recall is that the form of this molecule that I have shown here, which is not what you will always see, um, for instance, if you go to Wikipedia and look up amino acid structures, you're not going to see the molecule looking like this. I have drawn it where it's fully protonated because an amino acid, chances are, is in an aqueous environment. Um, Next up is I want to go to my titration curve. My y-axis of my titration curve is going to be my pH. My x-axis is going to be OH equivalence. So OH equivalence. So that would be there, there. And if you remember, this x-axis is 0 0.5, 1.0, 1.5, 2.0. So it's just a half and then a whole number, and then a half and then a whole number. Now, my y-axis ranges from 1 all the way up to 14. There are numbers in between those, obviously, but I'm going to make it a little bit simpler. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It got kind of crunched in there, but there it is. My first pKa value, my lowest pKa value is 2.20. That's going to be my first half marking. My next pKa value, my next highest pKa is 9.11. That's going to correspond to my next half value, which is 1.5. So I'm going to say that 1.5, and I'm going to draw a line, or I'm going to make a rough estimation straight up from that 1.5. Now I'm making my third from 2.5. And we're looking at right about there. So this gives me, I've got 3 pKa values, which means I'm going to have 3 horizontal regions of my titration curve. There's one horizontal region. Here's my second. There's my third. Now, these horizontal regions are also my buffering ranges, or my place where I can add more base, but my pH isn't going to change dramatically. So wherever you see a horizontal region of a titration curve where the y-axis is pH and x is OH equivalents, that's your buffering range. Now, with that in mind, there's my, not quite to my PI calculation, but that's the next thing that I want to do. So here's our different our titration curve. We have all these 3 points. Now, the next thing that I like to do whenever I have my titration curve is draw a dashed line from my half points, because that's going to give me kind of a nice way of saying, well, the predominant form, or this specific form is the predominant form in this region. So what we have over here on the right-hand side, my fully protonated form on my molecule, that is going to be the predominant form from 0 to 0.5. So this form of the molecule on the right-hand side is the predominant form from a pH of 0 to approximately 2.20. At 2.20, actually I have 50% of the molecule looks like this, and then the other 50% of the molecule looks like this. H3N. So my N termini is protonated. I've got my alpha carbon. My carboxylic acid is a carboxylate ion. My alpha carbon has a hydrogen. Then here's my R group, CH2, with my ring. And wait. Dun, dun, dun. So this is what the molecule looks like from a pH of 2.2 all the way up to, well, my next pK, which is 9.11. So within this range. Now, rather than redraw, I'm just going to update this form of my molecule, or this green model of my molecule. So I'm going to go to my eraser, erase. Now, I'm deprotonating my next group, which is the one with my lowest pKa, or my next lowest pKa. So that's going to go from NH2, or from NH3 plus to NH2. So this form of my molecule has a charge of -1. And this is the form that is predominant from the pH of 9.11 all the way up to 10.07. This is my -1. So I'll take a step back from pH of 2.2 to 9.11. That is the form of the molecule with a 0 charge. That's my Zwitter ion, because I have a positive and a negative charge simultaneously. My cation is from 0 to 0.5, or from 0 pH of 0 to 2.20. And then above 10.07 is where I will have my fully deprotonated form of my molecule, which I'm going to update the structure that I've got below. Rather than an OH, I have an O minus. So this is going to have a charge of -2. Okay. So that's the evolution of my molecule. Um, Now, with that said, if you were to, one, go about calculating the PI, how would you do that? Well, what you would do is the way that I've drawn it out here is I've come up with the possible charges for my molecule. Point or +1, 0, -1, -2. Each one of these arrows corresponds to a pKa. So 2.20, 9.11, 10.07. I'm going to take 2.20, add it to 9.11, so that'd be 11.31. Divide that by 2, and I get 5.65 approximately. That is the pH where my molecule, 100% of it is my Zwitter ion. 100% of it has a 0 charge. Okay, so that's an important thing that you should be able to do. You should be able to do that with any and every amino acid. Um, and so over the next few slides, I'm leaving those open for you to practice. What I would recommend doing is I would practice calculating all of these PIs, determining based on the pKa values, what are the possible charges? Draw that molecule and what are the possible charges that it can take. Then all that you do is you find the where, when you're listing out all the charges, you see something like this: +1 to 0, 0 to -1. What are the pKa's from +1 to 0 and from 0 to -1? Add those two, divide it by 2, or add those two pKa values, divide by 2. That's your PI. Now, another important skill that you need to be able to have is to be able to calculate or be able to visualize and draw the predominant form of the molecule at a specific pH. So let's say that my pH, I wanted to know the predominant form at a pH of 8.2. Well, this is actually a super easy and fast question for me because of having drawn out the pK or the titration curve. So all that I'm going to do is I'm going to say, all right, 8.2, that's approximately here. So that would mean I'm right here. Okay. Well, the predominant form of my molecule is going to have a 0 charge. And that's really all there is to that sort of question. So we've calculated isoelectric point. Here's aspartic acid. Let's go ahead and do a quick calculation for aspartic acid. Aspartic acid, as it's drawn here, has a charge of +1. It will go on to lose a proton here, so it'll have a 0 charge. Then, after that proton is lost, it will lose this proton. That will be -1. And then the last proton it will lose will be on the N termini, and that will give me a molecule with a charge of -2. Now, this is a triprotic acid. Aspartic acid is a single letter code of D. My lowest pKa is 2.10. That corresponds to my C termini. Check. The next pKa is 3.86. Is that R group? Check. And then last but not least is my N termini, 9.82. And that's my N termini right here. Check. So if I wanted to calculate my PI, I would say 2.10 plus 3.86 divided by 2 gives me 5.96 divided by 2 is 2. Let's see, 9.8, I think, approximately. Okay, so that's a quick way that you can do it. Having having the molecule drawn out and being able to identify those pKa values, assigning them is going to be very helpful. Now, individual amino acids can react with one another to form what's known as a peptide bond. Here, what we have is a model for that. Amino acid 1, amino acid 2. The C termini of one amino acid reacts with the N termini of another amino acid, and we form what is known as a peptide bond right here. Now, this is a condensation reaction because we produce water in the process, so water is lost. This peptide bond is important also because when we have this reaction take place, this is going to be two ionizable groups that we basically can ignore when it comes to any sort of charge or PI calculation. So here's another way of looking at it and what you would expect to see at an aqueous neutral pH. This group is going to be the carboxylate ion. This N termini is the positive charge. Those two are going to react with one another, and we can form something like this. Now, what I've drawn here is a peptide. This is known as a dipeptide, so it's two amino acids, YE. This is a tyrosine followed by a glutamic acid. Now, one of the things that I think is the natural progression from calculating a PI of an amino acid is calculating the PI of a polypeptide. We can look at the N termini and the C termini, then our different R groups. Okay, what I'm going to do is I'm going to look at this polypeptide and say, what is the overall charge of it? Well, the overall charge of this polypeptide is +1 because there's a positive charge right here, and then every other ionizable group is neutral. Now, if we look at Y and E respectively, let's take a look at the different pKa values that we need to be thoughtful of. Well, the N termini of tyrosine, Y, has a pKa of 9.11. So we're going to use that. We're going to assign that. Now, the C termini of tyrosine, 2.20. Well, if we look at the C termini of tyrosine, well, it's not actually a COOH, so it's not ionizing because it's a part of my peptide bond. And so this pKa, I'm going to scribble it out because I don't need it. Now, my R group with a pKa of 10.07, I do need, so I'll use that. So I'm going to write that in because that's still ionizing. Now, my next amino acid, well, I've got to go back to that peptide bond. That's where I'm going to find the N termini of the amino acid glutamic acid. And I'm going to see a 9.47. But this is just like the C termini of my previous amino acid. It's a part of a polypeptide. Excuse me, or it's a part of a peptide bond. So 9.47, I don't need to worry about that because that group is not ionizable. My peptide bonds are basically never going to be charged. Okay, so whenever I'm looking at a polypeptide, most of or if the functional group is found within a peptide bond, I can ignore it. Now, my R group for glutamic acid, I do have to think about that, 4.07. My C termini of glutamic acid, I also have to think about that. So that's accounted for. So what this is going to allow me to do is I'm going to go ahead and put together the entire charge profile. This polypeptide could never have a charge of +2 because the only other possible positively charged group is within my polypeptide bond. So this is going to go from +1 to 0. The first group that's going to be deprotonated is this one. I'm going to write first by it. Okay. Then after that group gets deprotonated, I'm going to go on to my second ionizable group. And that's going to have a pKa of 4.07. So I'm going to circle that. That's going to give me -1. My third ionizable group is going to have a pKa of 9.11. So that's my third group. That's going to give me a -2 charge when all three of those are deprotonated. And then my last ionizable group is going to be fourth, which is my 10.07. Now I've got four arrows, one, two, three, four, and I've got four pKa values. So I'll write 2.10, 4.07, 9.11, and 10.07. Forgot my last possible charge, which is -3. So this dipeptide can have a charge ranging from +1 all the way to -3. It's never going to be +2. It's never going to be -4 as it stands right here. Now, to calculate the PI of this, we do the exact same thing as if we're calculating the PI of a single amino acid. Take the two pKa values that flank the charge of 0, so 2.10 plus 4.07, that gets us 6.17 divided by 2 equals 3.17 divided by 2. Let's call it 0.085. There we go. That's how you calculate the PI. You look at all the different charges. Treat a peptide as basically the exact same thing as a single amino acid. And there you go. Now, there's some other important things to know about amino acids. Just like when we talked about sugars, we talked about L and D sugars. The difference is that D sugars are predominant, whereas L amino acids are the predominant form of your amino acids. Other amino acids have unique features in that they can absorb light within the UV range. So phenylalanine, tyrosine, and tryptophan all absorb light within the UV range. So that gives a way of detecting amino acids to tell whether or not there's protein in a solution. So phenylalanine, F is the single letter code for that, tyrosine, Y, and tryptophan, W. Those are the amino acids that have the capability of absorbing UV light. Now, one other amino acid that's worth knowing about is the amino acid cysteine. It has a unique feature. It's one of our two amino acids with sulfur in the side chain, cysteine and methionine. Now, cysteine has a thiol, or a sulfhydryl group, and these can undergo an oxidation reduction reaction where they form something known as cysteine, which is a disulfide bond. This is a covalent linkage. This is a strong bond between these two amino acid side chains. Now that's valuable because that's pretty darn unique. The way that other amino acids interact is going to be a little bit different. For instance, if you took something like glutamine or asparagine, that can interact with an amino acid like tryptophan or tyrosine, and that's going to be hydrogen bonding. We've also got amino acids with hydrocarbons. Well, those are going to be brought together by hydrophobic interactions. And then last but not least are amino acids like this, where we have a carboxylate ion and amine. That's going to be an ionic interaction. So what I'd like you to do with this is practice drawing, practice identifying, practice calculating overall charge ranges. One recommendation that I always have is to draw a peptide or put together the charge range for a peptide that's something like your name. So my name is Joel. Well, J doesn't correspond to a single letter code, nor does E. EL does. That would be glutamic acid and leucine. Put together glutamic acid and leucine and come up with what is the overall charge of this. Do something like that and try to visualize a titration curve. What I've got here is glutamic acid, which is a negatively charged residue, and leucine, which is a nonpolar residue. So what I'll do for this is I'll come up with a little box. This is my model that I use for calculating charges quickly. This side of the box right here corresponds to my N-termini. My N termini of glutamic acid, whenever it's fully protonated, it's going to have a positive one charge. My R group for glutamic acid is going to have no charge when it's fully protonated. Leucine is going to have no charge whatsoever, and the C termini is going to have no charge whatsoever. So I've quickly come up with my molecule can have a charge ranging from positive 1. Now what I'm going to do is I'm going to say this C termini of leucine, let's call that pK value 2.10. And then for glutamic acid, that's got an R group pK value of like 4.4 and then 9.5. So I've got my three ionizable groups, and leucine, it's not ionizable. So I'm going to say +1 to 0, 0 to -1, and then -1 to -2. That's going to be 2.1, 4.4, 9.5. 2.1 plus 4.4 is 6.5 divided by 2 would be 3.25 is my PI. I'm going to give you the pKa values. It's up to you to come up with good examples for this. And like I said, I would start with names or common words. Draw the peptide for draw the peptide for, let's see, snake. Um, Draw any sort of peptide and does every letter in that polypeptide work? And what does that polypeptide look like? All right, I hope that's helpful. Tomorrow we will continue. We'll be talking about protein structure and we'll go from there. All right, have a good one.